Welcome back. Welcome to the Lattice Cryptanalysis session, the session you've all been waiting for. And we're going to start with Xavier Bonnetin on the work with André Chailloux, André Schrottenlauer, and Encryption.
Thanks, Leo, for the introduction. So this work is called Finding Many Collisions via Quantum Works, an application to lattice sieving. And as the title said, the aim is to obtain efficient algorithm to find many collisions in a quantum setting. So first of all, I will present the classical landscape on collision finding before moving to quantum algorithms and our work. So how can we find collision classically? So we are doing collision finding in the random case. So we assume we have a function f from n bit to n bit, and we want to find two colliding inputs. So two different inputs that are mapped to the same output. And there's a very simple algorithm that achieves that, which is simple to take a large list with 2 to the n over 2 inputs, and you sort it according to the output of the function. And then you can efficiently extract collisions from the list. So this works with one list, but this also works with two lists, L1 and L2, with the same technique. So this is a very simple algorithm, and there have been some improvements that have been proposed, such as, for example, Pollar's rho, lambda method, etc. These methods are better because they are memoryless, they are parallelizable, but in terms of query complexity, they roughly achieve the same cost as this very simple list-based algorithm. Of course, in practice, these improved algorithms are the ones you want to work, but if you only care about query complexity or even just total number of operations, this simple algorithm does the same thing. We can also have a look at slightly different settings. For example, if you want to find more than one collision, say 2 to the t, then you can just take a larger list. If you multiply the list size by 2 to the t over 2, you can expect the list to contain 2 to the t collision, and the same algorithm works. If you have a function with an output size that is larger than its input size, then it is harder to find collision, but the same approach still holds. You take a larger list of size 2 to the t over 2 plus m over 2, with m the number of output bits, and it will contain the expected number of collisions we want 2 to the t. And so these are some very simple list-based algorithm, but there is a general query lower bound for classical collision finding, which actually matches this algorithm. That is, in a classical setting, if we only care about query complexity, everything is solved by just taking a large enough list. So now I will move to quantum computing, where the things are a bit more complicated. So first of all, when we talk about quantum collisions, there's one algorithm that comes to mind, which is the BHT algorithm for Brassard, Hoyer, and Tapp, which is a quantum improvement over this list-based algorithm. So the idea is still to take a large list, but instead of looking for some collision inside this list, you look for just another input, random, that collides with one element on the list. And you search for this input using a quantum search, because this will give you a quadratic speedup. And so the cost of this algorithm is, well, 2 to the u in memory, because you have this large classical list. And quantumly, you have 2 to the u, which is the cost to construct the list, plus the cost of the quantum search, which will be 2 to the n over 2 to the u is the probability, and you take the inverse of the probability, and you take the square root of that. And you can see that this balances at 2 to the n over 3. And if you want to find more than one collision, you can have pretty much the same approach, but by taking a largest list. So if you take a list of size 2 to the n over 3 plus 2/3 of t, then you can do 2 to the t quantum searches. These searches will cost less, but there is more of them, which will balance the cost with the fact that we had a larger list that is more expensive to to construct, and we have an overall algorithm with cost 2 to the n over 3 plus 2/3 of t. And in a way that is very similar to the classical setting, there is a general query quantum lower bound that has been proposed by Liu and Zandri in 2019, which tells us that any quantum algorithms that find 2 to the t collisions must have a cost of at least 2 to the m over 3 plus 2/3 of t. So this BHT algorithm and its variant actually match the lower bound when the output size is the same as the input size. And now the question is, what happens when the output is larger? And if the output is larger, so say you want to find one collision, you can still try to apply BHT algorithm with a larger list, say of size 2 to the m over 3, which is what the lower bound will give you. However, there is an issue with larger output, which is that you can't expect that for all inputs they will be part of a collision. Only a small fraction of all the inputs are part of a collision. So because we only have 2 to the 2n minus n collision overall on average. And for the algorithm to work, we need to have that in this list of size 2 to the m over 3, there is at least one input which is actually part of a collision. And if we compute the probability, we'll see that this imposes a restriction on the output size. That is, the output size must be at most 1.5 times the input size. So, of course, if we are not in this case, we can still make it work by taking a larger list. But in this case, we no longer match the lower bound. So if we want to summarize this algorithm, so this is a graph where the horizontal axis is the output size relative to the input size, so between n and 2n, and the vertical axis is the number of collisions in logarithm scale, so from 1 collision to 2 to the n collision. And with the previous slides, we've seen that BHT algorithm only tackles this blue triangle here, where it matches the lower bound. If we want to apply it outside of this triangle, for example, by taking larger list or by repeating the algorithm, we can still have an algorithm that works, but it would not be tight. It would have this worse complexity of 2 to the k plus m minus n. Now, if we want to do better than that, we'll have to slightly change the approach and use a quantum algorithm that built upon a quantum works framework that I will quickly present. And to present quantum work, I will first present the classical analog, which is classical random walk. And the idea is fairly simple. You see your search space as a graph in which you have nodes. You start at a random node, and then you do a random walk on the graph until you find a node that's good, that is, a node that contains the solution to your problem. So here, a node that contains a collision, for example. And if you have this framework, then you can study your random walk by introducing a few parameters. So first of all, well, P, which is the probability for a node to be good, which will be important. Another important parameter is so 1 over epsilon, so the inverse of the spectral gap, which is a graph theoretic notion. And the thing to have in mind is that it represents the number of steps of a quantum walk you need to do to go from one node to any other node. So if you walk 1 over epsilon times, you can reach any node in the graph. And in terms of complexity, we also have essentially 3 things we can do. First, we need to construct the first node to begin our work, so this is cost S. And then we have a cost to work, that we assume it is efficient, and a cost to test whether or not a node is marked. And from that, we can construct an algorithm which is just start with a random node. This will cost us S, and then we repeat 1 over p times a walk from the node we are at 1/epsilon times to arrive at another random node, plus a test to check if this new node we've obtained is marked. And so we obtain this complexity that's here. And as an application, we can do collision finding in this framework. So for that, we will work on a graph which is a Johnson graph. This is a graph where nodes are sets of 2 to the r elements among 2 to the n. And you work on this graph by removing one element in the set and replacing it by another element. And this graph has a lot of nice properties. And in particular, its spectral graph is known, and it is roughly 2 to the minus r, which is fairly intuitive. It means that if you do 2 to the r replacement on a set of size 2 to the r, you can obtain any set of size 2 to the r. And if we do our work on this Johnson graph, it means that we have to create a random list of size 2 to the r, which goes 2 to the r, and then we'll have to do a certain amount of times. We work 2 to the r times, and once we've arrived, we check whether the new node contains a collision. So the overall complexity is presented here, and we have a trade-off between the size of the list and the number of work steps we need to do in order to obtain a collision. So the list is of size 2 to the r, and the probability for a node to be marked is 2 to the 2r minus n. And so we obtain this complexity here, that is max of 2 to the r and 2 to the n minus r, which actually matches the complexity of a very simple classical algorithm, which is take a list of size 2 to the r. If it contains a collision, you've won. Otherwise, drop the list and take another list. So this algorithm is not that interesting. However, as it is presented in a random walk framework, we can improve it quantumly with quantum walks. So the general idea of quantum walk is to simulate a quantum search on a graph using a walk update operator. And so this has roughly the same parameters as classical walk. So here I present quantum walk in the MNRS framework. We use the same property as for classical walk. The only thing that changes is for the cost, where we have some gains due to quantum search. That is, instead of having to iterate 1/p times, we only iterate 1/square root of p times. And instead of having to do a walk 1/epsilon times in order to obtain a random node, we only need to do 1/square root of epsilon updates in our algorithm. So this gives us an improvement over the classical algorithm. And if we want to find collisions in this framework, then what we obtain is actually Ambainis' algorithm. So we have our function from n to m bit, and we want to find a collision. And to do so, we do a quantum walk in a Johnson graph. And so we have the same principles as for the classical walk. The only thing is that the cost will be lower. So instead of 2 to the r and 2 to the m minus r, we obtain a cost that is the max of 2 to the r and 2 to the square root of the classical cost. So 2 to the m/2 minus r/2. And here, this balances at 2 to the m/3, which is actually optimal because it matches the quantum lower bound. And now, the question is, what happens if we want to find more collisions? So the general idea is the same as the classical idea. Take a larger list and then amortize it to find more collisions. However, there are some issues. That is, at the end of the quantum walk, we measure to obtain the collision. And if we do so, we destroy the quantum state. So we cannot reuse this quantum memory. We would have to reconstruct it, which is not efficient. And so our aim in this work is to have a procedure that allows us to extract collision from the output of Ambainis' work and still have a useful quantum data structure that will allow us to extract more collisions afterward. And so for that, we have to change a bit the way we do our work. So we first begin with Ambainis' work, a normal quantum work on a Johnson graph. And then, in the end, when we have obtained the uniform superposition of nodes that contain a collision, we do a partial measurement on the number of collisions that we have. And we will remove reversibly from our quantum data structure this number of collisions. And that way, we measure these collisions. And that way, we will obtain still a quantum state that is still a uniform superposition of quantum data structures, but with a few constraints. First of all, as we've removed collisions, they are collision-free. And as we've removed some inputs that we've measured, they do not contain it. And from this quantum state, we can start a new quantum walk on a smaller Johnson graph, which is the same as before, but as we've removed some elements in the sets are slightly smaller, and the ambient set will be smaller because we don't want to walk back to the preimages we've removed. And there are a few assumptions in the algorithm I've just presented. The first one is that we have efficient history-independent operations, because in order to do a quantum walk, we need to have a unique quantum state that represents your node in your graph. This means that the quantum state must not depend on the order in which you've removed and added elements. And so to have efficient operations, we use a data structure that's built about radix tree. And to be history independent, what we do is we have a quantum memory layout, which is actually the uniform superposition of all classical layouts. So that way we have to change a bit or take care on how we do the update, but we can ensure that we have a unique quantum state. And the other assumption is that the next quantum walk needs to work. And for that, this means that, well, first, this is a technicality, but the things we obtain after the measurement must be a node, correspond to a node in a Johnson graph. But also, it must be OK to start from the nodes that do not contain any collision. And for this to be true, we need to have that the superposition of collision-free nodes is close to the uniform superposition of all nodes. Another way to see it is that, on average, a node does not contain collisions. Nodes with collisions are only a small fraction. And under this assumption, our algorithm works. And so if we come back to the triangle, we obtain this new result, where we have this new red part in which we are optimal. And as before, we can extend it with slightly worse complexity in this smaller triangle. The algorithm also works with golden collision. We can simply, if we add an additional assumption, it will also work. And here, the constraint on the number of collisions is only the constraint on the number of golden collision. So our algorithm has less issues if we want golden collision. And finally, I will shortly talk about quantum lattice sieving. The general idea of sieving is fairly simple. You start with many vectors, and you want to find some pairs such that their sum or difference are of smaller norm. And if you have enough pairs, you just iterate until you find the shortest vector. There has been recently some work on quantum lattice sieving that do that with a quantum work. And what they do is they use locality-sensitive filtering, which is an idea that comes from classical sieving. The idea is that you assume there is a code in the ambient space, and close vectors that will, whose form a pair that lead to a smaller norm, will tend, if you have a code, to decode to the same value. And this means that we can reduce lattice sieving to a problem of finding a collision on a function, the function being the decoding of a code. And of course, we need some efficiently decoding code, but this is what they do classically. And as we have a better quantum algorithm to find many collisions, we can improve the previous algorithm on lattice sieving, so from an exponent of 0.257 to a groundbreaking 0.2563. which is an improvement of roughly a third of a percent, but this is the best known exponent for lattice sieving, and this means we qualify for the lattice cryptanalysis section. Thank you all for your attention.
Any very brief question for our speaker? I have a lattice cryptanalysis question.
Okay.
There was a lower bound of Laroven and Kirsanova on those local density hashing techniques, and they claimed something for quantum that you disprove.
Well, it was already disproved by the previous quantum algorithm. They assumed a Grover-based algorithm, and here we use a quantum work. So this is how we can beat their lower bound.
And if you apply their technique, but to the more general framework, do you think that you can get a lower bound as well?
I guess so, but I have not studied that.
Well, if that's all, let's move to the next speaker. So the next talk will be given by Huck Bennett, and it is joint work with Atul Ganju, Pura Petal Tau Wai Chai, I'm very sorry, and Noah Stefan Davidovitz. Okay. And Huck is on the stage and ready.
Yeah, nice. Okay, so thank you very much for coming. So I'll be talking about, I'm Huck, I'll be talking about joint work with Atul Ganju, Pura Pitathawachai, who are both students at the time of this work, undergraduate students, and Noah Stevens Davidowitz, who's here. So I think probably most people in the audience know what a lattice is, so it's a regular grid of points in n-dimensional space, or more formally, it's the set of all integer linear combinations of some n linearly independent basis vectors. And when we concatenate these vectors together to form the columns of a matrix, then we get a basis matrix, capital B. So one thing that's important for this talk, and just as a reminder, so lattice bases are typically not unique, so if you're in at least 2 dimensions. And in particular, 2 bases generate the same lattice if you can multiply one of them by a unimodular matrix, that is an integer matrix whose determinant is plus or minus 1 to get the other basis. And the shortest vector problem, which is the most important computational problem on lattices, is given a basis of a lattice's input to find a shortest non-zero vector in the lattice, that is a vector whose norm is lambda 1. So the problem that I'll be talking about today is the lattice isomorphism problem. So intuitively, what the lattice isomorphism problem is, it says you get 2 different lattices as input, specified as bases, and your goal is to determine whether one lattice is a rotation of the other. In other words, if there's an orthogonal linear transformation O, that is a matrix, you can think of this in terms of matrices as an O such that O transpose O is the identity, such that O times the first lattice, L1, is equal to the second lattice, L2. So here, when we're specifying this in terms of bases, we have both an O and a U. So the computational question, is whether we can convert a basis B2 into B1 by left multiplying by our rotation O and right multiplying by some U, which is unimodular. So in fact, in this work, we're even just going to consider a special case of this, which has actually received a lot of attention, particularly in the last couple of years. So what we're going to do is we're going to fix the first lattice just to be the simplest lattice imaginable, just the integer lattice Zn. So in other words, you can think of B1 as just being In, the n-dimensional identity matrix. Okay, so here's kind of the picture. So this shows up, I guess, as reasonable size on the big screen. So on the left, we just have Zn. Again, you can think of the basis as just being the standard normal basis. And on the left, so we have a yes instance of the problem. So we have, on the right, we have some rotation of Zn along with a non-orthogonal basis of it. So first algorithmic question. Is there an efficient algorithm for solving this problem? So one thing to note here is it actually suffices to solve SVP on this class of lattices, on rotations of Zn. Because if we can find a shortest non-zero vector in a rotation of Zn, that'll be a unit vector, and we can just project orthogonally from that and recurse, and therefore recover all of O, all of an orthogonal basis of the rotation. So, and then there's the following cryptographic question, which is, okay, say that this problem is in fact hard, like there doesn't wind up being a fast algorithm for it, then can we build some cool cryptography from this assumption? So there's a whole bunch of related work on this, some of which I'll mention again later. But in terms of algorithms, there's been work that's happened for the last 20 years on this, and including some recent work just in the last few years. And in terms of cryptography, I think most people started off thinking that, okay, this is an easy question, this problem should be easy, so it would be silly to base cryptography on it. But more recently, we and others have taken the assumption, well, as spoiler for the next couple of slides, but we don't know any efficient algorithms for this problem. I'll talk about that more. But so, okay, say we run with this assumption that maybe this problem is in fact hard, what can we do with it? So results in our paper. So the first result is a provable 2 to the n over 2 time algorithm for ZSVP and hence for ZLIP. So, and this is actually, so it's still exponential, but this is the first speed up or non-trivial speed up over just the fastest generic algorithm for the shortest vector problem. And really the core to our algorithm is a reduction from the exact shortest vector problem on rotations of Zn, the ZSVP, to approximate unique SVP. So we have a polynomial time reduction from exact ZSVP to gamma USVP for any constant gamma greater than 1. And just one thing to note here, actually, so the algorithmic result in our paper doesn't just work for solving SVP on rotations of Zn. So it actually works for solving SVP on a much larger class of lattices called semi-stable lattices that don't have too large lambda 1. And so in terms of cryptography, we show how to build secure public key cryptography, assuming hardness of worst case variance of ZSVP. And finally, we give a provably hard distribution of bases of rotations of Zn and give extensive experiments for how hard it is to solve the shortest vector problem on lattices generating according to this distribution. And so the hard distribution of bases we show is generated via discrete Gaussian sampling, and this essentially resolves a question addressed by Blanks and Miller in 21, who gave a whole bunch of different algorithms for generating bases, hard bases of Zn. So related work. So in terms of algorithms, things that are directly related to what I want to talk about here, so Leo, who's sitting right here, came up with an algorithm for solving ZSVP that runs in the same time as the algorithm in our paper. So it runs in 2 to the n over 2 time, but it uses different techniques. And I think it's a really interesting question to see whether it's possible to combine our techniques and his techniques to do even better. In terms of cryptography, Ducas and Van Werden in 2022 gave a chem rather than a public key crypto system, but using similar assumptions and techniques. And so similarly, a number of previous papers had explored this idea of using discrete Gaussian sampling to generate hard lattice bases. And just backing up here, before I say any more details about what we did, one thing that I'd like for you to take away from this talk, as much as what we did, is that this family of problems is really interesting, and I think people should work on it more. So just the problems related to the lattice isomorphism problem, and the special case of it where one lattice is fixed to be Zn. So if you think it's easy, great, break it, come up with a fast algorithm for it. If you think it's hard, then build some cool crypto from it. Okay, so first, let's start with our reduction and algorithm for ZSVP. So I have a picture at the bottom, which will sort of just shows the main idea behind our reduction. But the main technique that we use is lattice sparsification. So what we do here, so this sparsification works for arbitrary lattices, but basically what you do is you have your input lattice and you sample a random sublattice of your input lattice of some specified index, say prime index q. And the way you can do this is you define LQ of A here. So you look at just, so if B is a basis of your input lattice, then you take the sublattice, which is formed by B of x, such that all the coefficient vectors x satisfy a random linear constraint mod q. And so our algorithm at a high level is actually quite simple. What we do is we repeatedly do this. We repeatedly sparsify our input lattice, so starting over each time. So we start with our input lattice, apply a random linear constraint to it to get a sublattice, and then we hope that what we get is an instance of approximate unique SVP. I'll define that in words in just a second, but if you know what it is. So we hope that we get an instance of approximate unique SVP as output. We feed that into an oracle for approximate unique SVP, and if we did correctly, in fact, get an instance of approximate unique SVP, then we will have typically solved our original shortest vector problem on a rotation of Zn. So what we're going to do is we're going to specifically, what we do is we start with a rotation of Zn, so that's what's shown on the left. And so what this red circle shows is a circle or ball in general of radius, like say, is slightly larger than 2, so between 2 and 3. So that's our gamma here. So the shortest vector which is lambda 1, the length of the shortest vector in a rotation of Zn, non-zero vector is of course 1. So what our goal is for this algorithm is to sparsify away everything except for all non-zero vectors, except for some shortest vector and integer combinations of it. So if you see what's in this picture here, so we keep on the right, so this shows a success, we keep one shortest vector, just sort of the short red vector there, and we delete all other vectors inside this red circle that are linearly independent of it. Okay, so this turns out to be an instance of, say, 2 or so unique SVP, which is what we need. So what is unique SVP? So gamma unique SVP says that if we have a vector v, which is the shortest non-zero vector in the lattice, so it has norm lambda 1, then all vectors in the lattice that are linearly independent of it have norm greater than gamma times lambda 1. Okay, so specifically what's summarized here is if we have a success if when sparsifying we keep a shortest non-zero vector in the lattice, that is a unit vector, and we get rid of all other vectors of norm less than gamma. So if you just sort of check parameters and plug in known results, then in fact, for any constant gamma, if you set parameters correctly, you can get this to happen with noticeable probability. So you only need to iterate this process a polynomial number of times. So the overall cost for our algorithm consists of a polynomial number of calls to a gamma USVP oracle, which we can instantiate with known results and get 2 to the n over 2 time algorithm overall. So I should say by combining a reduction from Lubachevsky and Machancho and an algorithm from Agrawal, Dadouche, Regev, Stevens, Davidowitz, we just get a 2 to the n over 2 time algorithm for like say 2 at USVP. Okay, so that's what I want to say about the algorithm. So I'll mention our crypto system briefly. So for our crypto system, we're just going to imagine that Alicia wants to send Bob 1 bit. So we're just going to see how to encrypt 1 bit. And here, so we're going to be working on a lattice, which is a rotation of Zn. And Alicia's public key is going to be a bad basis of L, and Bob's private key is going to be an orthogonal basis, a good basis of L. Intuitively, the way that Alicia is going to encrypt a bit, so she's going to choose her ciphertext by sampling a random point in space. So not a lattice point, but some point in space. And she's going to do this according to different distributions, depending on whether she wants to encrypt 0 or 1. So intuitively, if she wants to encrypt 0, she's going to choose a point close to the lattice, and if she wants to encrypt 1, she'll choose a point far from the lattice. And then to decrypt, Bob can just round using his good orthogonal basis to compute the distance exactly of the ciphertext point to the lattice. So I should say in our paper, we actually specify everything in terms of quadratic forms rather than rotations of Zn, which actually are nicer computationally. So you don't have to work with rotations, but this is what's going on, but translated back into lattices, which I find a little bit easier to think about. But the math is actually better with quadratic forms. Right, so just looking at encryption more formally. So I need one more lattice definition, which is that of a fundamental parallelepiped of a lattice basis. So the fundamental parallelepiped is just the set of all real linear combinations of the basis vectors where the coefficients are restricted to be between 0 and 1. So for example, you get a parallelogram like what's shown here in 2 dimensions, and you get some higher dimensional analog in n dimensions. Okay, so how does encryption work? And again, this is with respect to the bad basis. So if Alicia wants to encrypt a 0, what she does is she first samples a Gaussian vector x, so like from a low variance spherical Gaussian, and then she takes it modulo the parallelepiped, which means that she shifts her sampled x by lattice vectors until it lands in P of B. So there's going to be a unique lattice vector she can shift by to get her sampled x into P of B. And if she wants to encrypt 1, she simply samples a uniformly random vector inside P of B. Okay, so it's easy to show that in high dimensions, even though this might not be clear in 2 dimensions, there's highest statistical distance between the encryption distributions for 0 and 1 in the case when R is chosen to be sufficiently small. And there's a tension between choosing R to be small, in which case you get high statistical distance between these distributions, and taking R to be larger, which will lead to higher security, because these 2 distributions will look similar. So you can maybe sort of intuitively see that if you took a super high variance Gaussian and took it modulo the parallelepiped, it would look almost uniform. And we actually have good tools for analyzing the exact statistical distance between these distributions. This crypto system is actually secure, provably secure, if certain worst case problems that are related to ZSVP are hard in the worst case. So specifically, this crypto system is provably secure if it's hard to distinguish a rotation of Zn from either a lattice who's with lambda 1 greater than square root of n log n, or a lattice that has a small smoothing parameter compared to Zn. And just a couple of last slides, so this is just building intuition for what the encryption distributions look like with respect to both the good basis, which is the secret key, and the bad basis, which is the public key. So this is what, if you're imagining sampling a Gaussian just kind of around the origin and taking it modulo the square, so here we're thinking of Z2 itself, you get something like this. So this is a plot of the PDF that you get. So like the orange part's showing that you get highly concentrated around lattice points. And yeah, last slide. And in the other case, sort of if you have a bad basis, then you get something like this, and it's more mixed up where the, like when you're encrypting 0, it's more mixed up where your ciphertext lands with respect to the corners of the parallelogram. And to make Leo happy, that's it. No, that was the end anyway.
I listened to a half an hour more of that, but unfortunately we have constraint. A quick question for Huck. Actually, it's a good paper. I don't have questions.
Yeah.
Ah, yes. Thank you.
Please.
A little bit more intuition about what it means to take some value modulo a parallel pipette.
Yeah, so you can see, so here you can imagine that if you shift this parallelogram around by lattice points, then you'll tile all of space. And in fact, each point in Rn will uniquely lie in some shift of the parallelepiped. So what that means is that if you sample an arbitrary point in Rn, then there will be a unique lattice vector you can shift by to put that point, which is like x here, into P of B.
Oh, I see. So does that mean that you're not associating each point in the overall vector space with a specific point within your parallel pipette?
Well, there's like a class of points. Like it'll be like a coset of or something that all get maps to the same point in P of B. Yeah, but like just the support of both of these distributions, like of the encryption of 0 and the encryption of 1, is just P of B itself. Again, it's given in terms of quadratic form, so it looks a little different in our paper, but it's the same thing, just adopted into that language.
Well, let's thank Huck and Xavier, and let's go get coffee.